Welcome to Unit 4, Environmental Geosciences. In this lecture, we will discuss the origin and internal structure of the Earth, an important topic for UGC NET Environmental Science. The Earth is believed to have originated about 4.6 billion years ago from the solar nebula according to the nebular hypothesis. During its early stages, the Earth was in a molten state. Due to differences in density, heavier elements such as iron and nickel moved towards the center, while lighter materials rose upward. This process is known as primary geochemical differentiation. As a result, the Earth became divided into four major components: the core, mantle, crust, atmosphere, and hydrosphere. The core forms the innermost part of the Earth and is mainly composed of iron and nickel. Surrounding the core is the mantle, which consists of silicate minerals rich in magnesium and iron. The outermost solid layer is the crust, which forms continents and ocean floors. The atmosphere developed through volcanic outgassing, while the hydrosphere was formed by the condensation of water vapor as the Earth cooled. From the geophysical point of view, the Earth consists of four layers: the crust, mantle, outer core, and inner core. Each layer has distinct physical and chemical properties. Understanding the origin, differentiation, and internal structure of the Earth provides the foundation for studying plate tectonics, earthquakes, volcanism, and other geological processes. These concepts are frequently asked in UGC NET examinations. Now, let's move to the next topic: minerals, rocks, and the rock cycle. Let us begin with minerals. A mineral is a naturally occurring, inorganic solid having a definite chemical composition and an orderly internal crystal structure. Minerals are the fundamental building blocks of rocks. Minerals possess several physical properties such as color, streak, luster, hardness, cleavage, and density. Their chemical properties include composition, solubility, and reactivity. Based on their origin, rocks are classified into three major types: igneous rocks, sedimentary rocks, and metamorphic rocks. Igneous rocks are formed by the cooling and solidification of magma or lava. They are known as primary rocks. Examples include granite and basalt. Sedimentary rocks are formed through the deposition, compaction, and cementation of sediments. These rocks often contain fossils, and examples include sandstone, limestone, and coal. Metamorphic rocks are produced when pre-existing rocks are subjected to high temperature and pressure, causing changes in their texture and mineral composition. Common examples are marble and gneiss. Now, let us understand the rock cycle. The rock cycle is a continuous process through which one type of rock is transformed into another. When magma cools and solidifies, igneous rocks are formed. Through weathering, erosion, transportation, deposition, and lithification, igneous rocks can be converted into sedimentary rocks. Under conditions of high temperature and pressure, sedimentary or igneous rocks are transformed into metamorphic rocks. If metamorphic rocks melt, magma is formed again, completing the cycle. Thus, the rock cycle demonstrates that rocks are dynamic and continuously recycled within the Earth's crust. For UGC NET examination, remember that Bowen's reaction series explains the sequence of mineral crystallization from magma and is one of the most frequently asked concepts from this topic. Landforms are natural physical features present on the Earth's surface. Their formation is controlled by two major categories of processes: endogenic processes and exogenic processes. Endogenic processes originate from within the Earth and derive energy from the Earth's interior. These processes include tectonism, volcanism, earthquakes, and mountain building. They are responsible for the creation of large-scale landforms such as mountains, plateaus, and rift valleys. In contrast, exogenic processes operate at the Earth's surface and derive energy mainly from solar radiation and gravity. These processes include weathering, erosion, transportation, and deposition. They continuously modify and reshape the landforms created by internal forces. Now, let us understand the plate tectonic theory, which forms the foundation of modern geology. According to the plate tectonic theory, proposed during the 1960s, the Earth's lithosphere is divided into several rigid plates. These lithospheric plates float and move slowly over the semi-molten asthenosphere due to convection currents present within the mantle. The movement of these tectonic plates is responsible for earthquakes, volcanic activities, continental drift, seafloor spreading, and the formation of mountains and ocean basins. Before the development of plate tectonics, Alfred Wegener proposed the continental drift theory in 1912. According to this theory, all continents were once united into a single supercontinent called Pangaea, which later broke apart and drifted to their present positions. Further evidence supporting plate tectonics came from Harry Hess, who proposed the theory of seafloor spreading. According to this concept, new oceanic crust is continuously formed at mid-oceanic ridges and destroyed at subduction zones. Based on the relative movement of plates, three major types of plate boundaries are recognized. The first type is the divergent boundary. At divergent boundaries, plates move away from each other. Magma rises from the mantle, cools, and forms new crust. These boundaries are constructive in nature because they create new lithosphere. Examples include the Mid-Atlantic Ridge and the East African Rift Valley. The second type is the convergent boundary. At convergent boundaries, plates move towards each other. Depending on the nature of the colliding plates, subduction or mountain building occurs. These boundaries are destructive because old crust is consumed. Examples include the Andes Mountains, the Himalayas, and the Japan Trench. The third type is the transform boundary. At transform boundaries, plates slide horizontally past one another. These boundaries neither create nor destroy crust, but they generate powerful earthquakes due to frictional resistance. Examples include the San Andreas Fault in California and the North Anatolian Fault in Turkey. Another important process associated with plate tectonics is mountain building, also known as orogeny. Most mountains are formed at convergent plate boundaries due to compressional forces. Fold mountains are formed by compression and folding of rocks. Examples include the Himalayas and the Alps. Block mountains are formed due to faulting. Examples include the Vosges Mountains and the Black Forest Mountains. Volcanic mountains are produced by volcanic eruptions. Examples include Mount Fuji and Mount Kilimanjaro. Besides tectonic forces, climate also plays an important role in controlling the formation and evolution of landforms. In arid regions, wind erosion produces desert landforms such as sand dunes and yardines. In humid regions, rivers are the dominant agents and form valleys, floodplains, and deltas. In glacial regions, moving ice creates characteristic features such as U-shaped valleys, cirques, moraines, and fjords. Thus, climate significantly influences the rate of weathering, erosion, transportation, and deposition, ultimately controlling landscape development. For UGC NET examination, remember the important keywords associated with this topic. Lithosphere and asthenosphere. Continental drift theory proposed by Alfred Wegener. Seafloor spreading theory proposed by Harry Hess. Constructive, destructive, and conservative plate boundaries. Orogeny and mountain building. Climatic controls on landform development. These concepts are frequently asked in both NET and JRF examinations. The Earth receives energy from the Sun in the form of shortwave solar radiation. This incoming energy is called insolation, which stands for incoming solar radiation. The amount of solar energy received at the outer boundary of the atmosphere on a surface perpendicular to the Sun's rays is known as the solar constant. Its average value is approximately 1361 watts per square meter. However, not all incoming radiation reaches the Earth's surface. A portion of solar radiation is reflected back into space by clouds, atmospheric particles, and the Earth's surface. This reflected fraction is known as albedo. The remaining radiation is absorbed by the atmosphere and the Earth's surface, causing heating of the planet. The concept of energy budget refers to the balance between incoming solar radiation and outgoing terrestrial radiation. In a state of equilibrium, the amount of energy received by the Earth is equal to the amount of energy lost to outer space. This condition is called steady state or dynamic equilibrium. Approximately 30% of incoming solar radiation is reflected back to space, while about 70% is absorbed by the atmosphere, oceans, and land surface. The absorbed energy is later emitted in the form of long-wave terrestrial radiation. Certain gases present in the atmosphere, known as greenhouse gases, absorb and re-emit this outgoing infrared radiation. This process is called the greenhouse effect. Major greenhouse gases include carbon dioxide, methane, nitrous oxide, water vapor, and ozone. The natural greenhouse effect maintains Earth's average temperature and makes life possible. However, excessive concentrations of greenhouse gases enhance this effect and lead to global warming. Now let us discuss the Earth's thermal environment. The thermal environment of the Earth depends upon the continuous exchange of energy between the Sun, atmosphere, oceans, and land surface. The distribution of heat is not uniform because different regions receive different amounts of solar radiation. Equatorial regions receive maximum insolation and are warmer, while polar regions receive lower insolation and remain cold. The unequal heating of the Earth creates pressure differences and drives atmospheric circulation and ocean currents. Next, let us understand the seasons. Seasons are caused mainly by the inclination of the Earth's axis and the revolution of the Earth around the Sun. The Earth is tilted at an angle of 23.5 degrees with respect to the plane of its orbit. As the Earth revolves around the Sun, different parts of the planet receive varying amounts of sunlight throughout the year, resulting in seasonal changes. It is important to remember that seasons are not caused by changes in the distance between the Earth and the Sun. There are 4 important positions of the Earth during its revolution. The first is the vernal equinox, which occurs around 21st March. During this time, the Sun is directly overhead at the equator and day and night are equal throughout the world. The second is the summer solstice, which occurs around 21st June. At this time, the Sun is overhead at the Tropic of Cancer, and the northern hemisphere experiences its longest day. The third is the autumnal equinox, occurring around 23rd September, when once again day and night are equal all over the world. The fourth is the winter solstice, occurring around 22nd December. During this period, the Sun is overhead at the Tropic of Capricorn, and the northern hemisphere experiences its shortest day. Besides axial tilt and revolution, several factors influence seasonal variations. These include the distribution of land and water, altitude, ocean currents, latitude, and atmospheric circulation patterns. For UGC NET examination, remember the following important concepts: solar constant, insolation, short wave and long wave radiation, albedo, energy budget of the Earth, steady state and dynamic equilibrium, greenhouse effect, Earth's thermal environment, axial tilt of 23.5 degrees, vernal equinox and autumnal equinox, summer solstice and winter solstice, climate of India and the phenomenon of ENSO, which stands for El Niño Southern Oscillation. These topics are highly important from the UGC NET and JRF examination perspective and are frequently asked in conceptual as well as statement-based questions. India experiences a tropical monsoon climate characterized by distinct seasons and considerable variations in temperature and rainfall. The climate of India is influenced by several geographical and atmospheric factors. The first factor is latitude. Since the Tropic of Cancer passes through the middle of the country, India experiences both tropical and subtropical climatic conditions. The second factor is altitude. Temperature decreases with increase in altitude, which explains why mountainous regions remain cooler than the plains. The third factor is distance from the sea. Coastal regions experience moderate temperatures due to the maritime influence, whereas inland regions experience extreme climatic conditions, known as continentality. Another important factor is the Himalayan mountain range. The Himalayas act as a climatic barrier and prevent the cold winds of Central Asia from entering India. They also obstruct the southwest monsoon winds and enhance rainfall over the Indian subcontinent. Ocean currents, pressure systems, jet streams, and western disturbances also play significant roles in determining the climate of India. Now let us discuss the Indian monsoon system. The word monsoon is derived from the Arabic word mausam, meaning season. Monsoon refers to the seasonal reversal of winds accompanied by changes in rainfall patterns. The Indian monsoon consists mainly of two phases, the southwest monsoon and the northeast monsoon. The southwest monsoon is the principal rainy season in India. During summer, intense heating of the Indian landmass creates a low-pressure area over northwestern India, while high pressure develops over the Indian Ocean. As a result, moisture-laden winds blow from the ocean towards the land, bringing heavy rainfall. The southwest monsoon reaches Kerala around the first week of June and gradually advances northward across the country. These winds divide into two branches. The first is the Arabian Sea branch, which provides heavy rainfall to the Western Ghats and Western India. The second is the Bay of Bengal branch, which moves towards northeastern India and the Indo-Gangetic plains. By September, the southwest monsoon begins to withdraw from northwestern India. The second phase is the northeast or retreating monsoon. During winter, high pressure develops over the Indian landmass and winds blow from land towards the ocean. These winds bring rainfall mainly to Tamil Nadu and the southeastern coast of India. Another important feature affecting the climate of India is the western disturbances. Western disturbances are temperate cyclones originating over the Mediterranean region. They travel eastward with the westerly winds and bring winter rainfall and snowfall to northwestern India. States such as Jammu and Kashmir, Himachal Pradesh, Punjab, Haryana, Rajasthan, and Uttar Pradesh receive precipitation due to western disturbances. These rains are extremely beneficial for rabi crops, particularly wheat. Now let us discuss droughts. Drought refers to a prolonged period of abnormally low rainfall resulting in water scarcity. India is highly dependent on monsoon rainfall, and therefore any failure or irregularity of monsoon can lead to drought conditions. Regions such as Rajasthan, Marathwada, Rayalaseema, Bundelkhand, and parts of Gujarat are frequently affected by droughts. One of the most important global climatic phenomena influencing Indian rainfall is ENSO, or El Niño Southern Oscillation. ENSO is a coupled ocean atmosphere phenomenon occurring over the equatorial Pacific Ocean. It consists of two opposite phases known as El Niño and La Niña. El Niño represents the warm phase of ENSO. During El Niño conditions, sea surface temperatures in the central and eastern Pacific Ocean become abnormally warm. Trade winds weaken, and the normal water circulation becomes disturbed. As a result, monsoon rainfall over India tends to weaken, often leading to drought conditions and reduced agricultural productivity. Examples of severe El Niño years include 1982, 1997, and 2015. In contrast, La Niña represents the cold phase of ENSO. During La Niña conditions, sea surface temperatures in the central and eastern Pacific Ocean become cooler than normal. Trade winds strengthen, and water circulation intensifies. Consequently, India generally receives stronger monsoon rainfall, which may sometimes result in floods. The atmospheric component associated with ENSO is called the Southern Oscillation. The Southern Oscillation refers to fluctuations in atmospheric pressure between Tahiti and Darwin, Australia. These pressure differences are measured using the Southern Oscillation Index, or SOI. A negative SOI value is generally associated with El Niño conditions, whereas a positive SOI value indicates La Niña conditions. Another important concept associated with ENSO is water circulation. Water circulation is an east-west atmospheric circulation over the tropical Pacific Ocean. Variations in this circulation are responsible for the development of El Niño and La Niña events. For UGC NET examination, remember the following important concepts. Factors affecting the climate of India. Mechanism of southwest and northeast monsoon. Arabian Sea branch and Bay of Bengal branch. Western disturbances and their role in winter rainfall. Drought-prone regions of India. ENSO cycle. El Niño and La Niña. Water circulation. Southern Oscillation Index or SOI. Effects of ENSO on Indian monsoon and agriculture. Let us begin with weathering. Weathering refers to the in situ disintegration and decomposition of rocks and minerals at or near the Earth's surface under the influence of physical, chemical, and biological processes. Unlike erosion, weathering does not involve the movement of materials. It only breaks down rocks into smaller particles, providing the parent material for soil formation. Weathering is broadly classified into three types: physical weathering, chemical weathering, and biological weathering. First, let us discuss physical weathering. Physical weathering, also known as mechanical weathering, involves the breakdown of rocks without altering their chemical composition. Several processes are responsible for physical weathering. Temperature variation causes expansion and contraction of rocks, leading to exfoliation and disintegration. Frost action occurs when water enters cracks in rocks, freezes, and expands, causing the rocks to break apart. Salt crystallization is common in arid regions where salts accumulate in rock pores and exert pressure on surrounding materials. Abrasion by wind, water, and glaciers also contributes to mechanical weathering. Next, let us discuss chemical weathering. Chemical weathering involves decomposition of rocks through chemical reactions, resulting in the formation of new minerals and soluble substances. One important process is solution, where minerals dissolve in water. Hydration refers to the addition of water molecules to minerals, leading to expansion and weakening. Hydrolysis involves the reaction between minerals and water, producing secondary minerals such as clay. Oxidation occurs when oxygen reacts with iron-containing minerals, forming iron oxides and giving rocks a reddish appearance. Carbonation results from the reaction between carbon dioxide dissolved in water and minerals like calcium carbonate. This process is responsible for the formation of limestone caves and karst topography. Chemical weathering is most active in warm and humid climates. The third type is biological weathering. Biological weathering is caused by living organisms such as plants, animals, bacteria, fungi, and lichens. Plant roots penetrate rock cracks and exert pressure, causing mechanical breakdown. Burrowing animals expose fresh surfaces to weathering. Microorganisms and lichens produce organic acids that accelerate chemical decomposition. After weathering, the loosened materials are removed by the process known as erosion. Erosion refers to the detachment and removal of weathered materials by agents such as running water, wind, glaciers, and waves. The eroded materials are then carried from one place to another through transportation. Transportation may occur in four forms. Solution involves dissolved substances carried by water. Suspension refers to fine particles remaining suspended in flowing water. Saltation is the movement of sand-sized particles through bouncing. Traction involves rolling or sliding of larger particles along the surface. Eventually, transported materials settle down through the process called deposition. Deposition occurs when the transporting medium loses energy and sediments accumulate in new locations. Examples include river deltas, floodplains, sand dunes, beaches, and glacial moorings. Now let us discuss soil formation. Soil is a natural body consisting of minerals, organic matter, water, air, and living organisms capable of supporting plant growth. The process of soil formation is known as pedogenesis. Soil develops gradually through the interaction of climate, organisms, relief, parent material, and time. These five factors are collectively known as the CLOPET model. C stands for climate. L represents living organisms. O represents organisms. R stands for relief or topography. P represents parent material. T represents time. Climate is considered the most important factor because temperature and rainfall regulate weathering and organic matter decomposition. Parent material determines the mineral composition and texture of soil. Topography affects drainage and erosion. Living organisms contribute organic matter and nutrient cycling. Time determines the degree of soil development. During soil formation, weathered rock particles combine with organic matter to produce a layer called regolith. Continuous weathering and biological activity eventually lead to the development of distinct soil horizons. The vertical arrangement of these horizons is called the soil profile. The O horizon is rich in organic matter and humus. The A horizon, also called topsoil, contains minerals and organic matter and is highly fertile. The E horizon is the zone of alluviation where minerals are leached downward. The B horizon is the subsoil and is characterized by accumulation of clay, iron, and aluminum compounds through alluviation. The C horizon consists of partially weathered parent material. The R horizon represents unweathered bedrock. Soil formation is an extremely slow process. It may require hundreds to thousands of years for a mature soil profile to develop. From the environmental perspective, soils perform several important functions. They support plant growth and agriculture. They store and filter water. They recycle nutrients. They provide habitat for numerous organisms. They regulate the hydrological cycle and contribute to ecosystem stability. For UGC NET examination, remember the following important concepts. Definition of weathering. Difference between weathering and erosion. Types of weathering. Chemical weathering reactions including hydration, hydrolysis, oxidation, carbonation, and solution. Agents of erosion and transportation. Forms of transportation namely traction, saltation, suspension, and solution. Deposition processes. Pedogenesis. Cloaked factors of soil formation. Regolith. Soil profile and soil horizons. Alluviation and illuviation. Now we shall discuss clay minerals, soil physical and chemical properties, soil types, climate control on soil formation, and the concept of cation exchange capacity. These topics are extremely important for UGC NET and JRF examinations and are frequently asked in conceptual and statement-based questions. Let us begin with clay minerals. Clay minerals are secondary minerals formed mainly through chemical weathering of primary silicate minerals. They are extremely fine particles, generally less than 2 micrometers in size, and possess large surface area and negative charges. These characteristics enable clay minerals to retain nutrients and water, thereby playing an important role in soil fertility. Based on their crystal structure, clay minerals are classified into different groups. The first and most important clay mineral is kaolinite. Kaolinite belongs to the 1:1 layer silicate group. It consists of one silica tetrahedral sheet and one alumina octahedral sheet. Kaolinite exhibits low cation exchange capacity and low shrink-swell behavior. It is commonly found in highly weathered tropical soils and is relatively stable. The second clay mineral is illite. Illite belongs to the 2:1 layer silicate group. It contains 2 silica sheets enclosing one alumina sheet. Illite possesses moderate cation exchange capacity and moderate swelling characteristics. It is abundant in temperate soils. Another important clay mineral is montmorillonite, which belongs to the smectite group. Montmorillonite also has a 2:1 layer structure but exhibits very high cation exchange capacity and remarkable swelling and shrinking behavior. Because of its ability to absorb large quantities of water, it is responsible for the expansion and contraction of black cotton soils. Vermiculite is another 2:1 type clay mineral with high cation exchange capacity and excellent nutrient retention properties. Among these minerals, montmorillonite possesses the highest swelling capacity and one of the highest cation exchange capacities. Now let us discuss soil properties. Soil properties are broadly classified into physical properties and chemical properties. The physical properties include texture, structure, porosity, permeability, bulk density, particle density, water holding capacity, and color. Soil texture refers to the relative proportion of sand, silt, and clay particles. Based on texture, soils may be sandy, silty, clayey, or loamy. Loamy soils are generally considered ideal for agriculture because they possess balanced proportions of sand, silt, and clay. Soil structure refers to the arrangement of soil particles into aggregates. Porosity indicates the percentage of pore spaces within the soil, while permeability describes the ease with which water moves through the soil profile. Bulk density is defined as the mass of dry soil per unit volume and is an important indicator of soil compaction. Water holding capacity refers to the ability of soil to retain moisture for plant use. Now let us examine the chemical properties of soil. One important parameter is soil pH. Soil pH determines the acidity or alkalinity of soil and influences nutrient availability. Most crops grow best in slightly acidic to neutral soils having pH values between 6 and 7. Organic matter contributes nutrients and improves soil structure. Essential nutrients present in soils include nitrogen, phosphorus, potassium, calcium, magnesium, sulfur, and various micronutrients. Electrical conductivity is another important property and indicates the concentration of soluble salts in soil. Excessive salinity adversely affects plant growth and productivity. Let us now discuss soil types. Different climatic and environmental conditions give rise to various soil types. Alluvial soils are highly fertile and are widely distributed in the Indo-Gangetic plains. Black soils, also known as regur soils, are rich in clay and are suitable for cotton cultivation. Red soils derive their color from iron oxides and are common in southern and eastern India. Laterite soils are highly weathered soils formed under high temperature and heavy rainfall conditions. Desert soils occur in arid regions and contain low organic matter. Mountain soils are found in hilly areas and support forest vegetation. Peaty and marshy soils are rich in organic matter and are generally waterlogged. Now let us understand the influence of climate on soil formation. Climate is considered the most important factor controlling soil formation because it regulates weathering, decomposition of organic matter, and leaching processes. Warm and humid climates accelerate chemical weathering and lead to the formation of deeply weathered soils such as laterites. Cold climates slow down weathering processes and result in shallow soils. Arid climates favor physical weathering and accumulation of salts due to low rainfall. Thus, temperature and precipitation strongly influence soil characteristics and distribution. Next, we come to one of the most important topics in soil science, namely cation exchange capacity or CEC. Cation exchange capacity is defined as the ability of soil to absorb and exchange positively charged ions, known as cations. These cations include calcium, magnesium, potassium, sodium, ammonium, and hydrogen ions. Clay particles and humus poses negative charges on their surfaces, which attract and hold positively charged nutrient ions. Plants absorb these nutrients from the soil solution through ion exchange mechanisms. Therefore, cation exchange capacity is a measure of the nutrient holding capacity and fertility of soil. The unit of CEC is centimoles of positive charge per kilogram of soil, represented as centimoles per kilogram. Several factors influence cation exchange capacity. The amount and type of clay minerals present in soil. Organic matter content. Soil pH. Degree of weathering. Soils rich in organic matter and clay generally poses high CEC and are more fertile. Among clay minerals, montmorillonite exhibits the highest CEC, whereas kaolinite possesses comparatively lower CEC. High CEC soils retain nutrients efficiently and reduce nutrient losses through leaching. Low CEC soils lose nutrients rapidly and require frequent fertilization. For UGC NET examination, remember the following important concepts. Classification of clay minerals. 1:1 and 2:1 layer silicates. Kaolinite, illite, montmorillonite, and vermiculite. Soil physical and chemical properties. Major soil types of India. Climate control on soil formation. Definition and significance of cation exchange capacity. Factors affecting CEC. Relationship between clay minerals and nutrient retention. Among the clay minerals, Montmorillonite has the highest swelling capacity and highest cation exchange capacity, making it one of the most frequently asked concepts in UGC NET and JRF examinations. Let us begin with geochemistry. Geochemistry is the branch of earth science that deals with the chemical composition of the earth and the distribution, migration, and cycling of chemical elements within the lithosphere, hydrosphere, atmosphere, and biosphere. It helps us understand the origin, abundance, and behavior of elements and the chemical processes operating within the Earth system. Elements are not distributed randomly. Their abundance and distribution depend upon their chemical properties and geochemical behavior. Now let us discuss the geochemical classification of elements. Based on their affinity for particular phases and reservoirs, elements are classified into 4 major groups according to Goldschmidt's classification. The first group is lithophile elements. Lithophile means rock-loving elements. These elements have a strong affinity for oxygen and are concentrated mainly in the Earth's crust and silicate minerals. Examples include oxygen, silicon, aluminum, calcium, sodium, potassium, magnesium, and titanium. The second group is siderophile elements. Siderophile means iron-loving elements. These elements possess affinity for metallic iron and are concentrated mainly in the Earth's core. Examples include iron, nickel, cobalt, platinum, and gold. The third group is chalcophile elements. Chalcophile means sulfur-loving elements. These elements combine readily with sulfur and occur mainly in sulfide minerals. Examples include copper, zinc, lead, mercury, cadmium, and silver. The fourth group is atmophile elements. Atmophile means gas-loving elements. These elements are concentrated in the atmosphere and hydrosphere. Examples include nitrogen, hydrogen, helium, argon, and noble gases. Goldschmidt's classification is one of the most frequently asked topics in UGC NET examinations. Now let us discuss the abundance of elements. The Earth's crust is dominated by 8 major elements. Oxygen is the most abundant element and constitutes approximately 46.6% of the Earth's crust. Silicon is the second most abundant element and accounts for about 27.7%. Together, oxygen and silicon form more than 74% of the Earth's crust. Other important elements include aluminum, iron, calcium, sodium, potassium, and magnesium. The abundance of elements differs among various Earth reservoirs. In the core, iron and nickel dominate. In the mantle, magnesium and iron-rich silicates are abundant. In the hydrosphere, oxygen and hydrogen are predominant. In the biosphere, carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur are essential elements. Let us now understand geochemical recycling. Elements continuously circulate among the atmosphere, hydrosphere, lithosphere, and biosphere through various biogeochemical cycles. This continuous movement of elements is known as geochemical recycling. The water cycle or hydrological cycle describes the movement of water through evaporation, condensation, precipitation, infiltration, and runoff. The carbon cycle regulates the movement of carbon between the atmosphere, oceans, soil, rocks, and living organisms. Carbon dioxide is removed from the atmosphere by photosynthesis and returned through respiration, decomposition, and combustion. The nitrogen cycle involves fixation, nitrification, assimilation, ammonification, and denitrification. Nitrogen-fixing bacteria convert atmospheric nitrogen into forms usable by plants. The phosphorus cycle differs from other cycles because it lacks a significant gaseous phase. Phosphorus is released from rocks through weathering and enters ecosystems where it is utilized by living organisms before returning to sediments. These biogeochemical cycles maintain ecological balance and ensure the continuous availability of nutrients. Now let us discuss paleoclimate. Paleoclimate refers to the study of Earth's climate during geological time periods. Since direct measurements are unavailable for ancient climates, scientists rely on proxy indicators to reconstruct past climatic conditions. One important proxy is ice cores. Ice cores obtained from polar ice sheets contain trapped air bubbles that provide information about atmospheric carbon dioxide concentration and temperature variations. Tree rings are another important proxy. The width and density of tree rings reveal information regarding rainfall and temperature conditions during different years. Marine sediments preserved on the ocean floor provide evidence of past oceanic productivity and climate changes. Pollen grains preserved in sediments help reconstruct ancient vegetation and climatic conditions. Stable isotopes, particularly oxygen isotopes and carbon isotopes, are extensively used in paleoclimatic studies. Variations in oxygen isotope ratios provide information about past temperatures and glacial cycles. Paleoclimate studies are important because they help us understand natural climate variability and improve predictions of future climate change. They also provide evidence regarding glacial and interglacial periods and long-term environmental changes. Now let us summarize the importance of geochemistry. Geochemistry helps explain the origin and distribution of elements in Earth systems. It supports mineral exploration and energy resource studies. It contributes to soil fertility, agriculture, and water quality assessment. It plays a vital role in environmental monitoring and pollution studies. Paleoclimate research provides valuable information for understanding present and future climate change. For UGC NET examination, remember the following important concepts. Definition and scope of geochemistry. Goldschmidt's classification of elements. Lithophile, siderophile, chalcophile, and atmophile elements. Abundance of elements in the Earth's crust. Major elements of the lithosphere, hydrosphere, and biosphere. Geochemical recycling. Water cycle, carbon cycle, nitrogen cycle, and phosphorus cycle. Proxy indicators of paleoclimate. Ice cores, tree rings, marine sediments, pollen grains, and stable isotopes. Significance of paleoclimate studies. These concepts are highly important and are frequently asked in UGC NET and JRF examinations. Let us begin with the distribution of water on Earth. Water is one of the most essential natural resources and covers nearly 71% of the Earth's surface. However, most of this water is saline. Approximately 97% of the Earth's water is present in oceans and seas and is unsuitable for direct human consumption. Only about 3% constitutes freshwater. Out of this freshwater, nearly 68% is stored in glaciers and ice caps, around 30% exists as groundwater, and less than 1% is available in rivers, lakes, wetlands, and the atmosphere. Thus, groundwater represents the most important source of freshwater for human use. Hydrology is the science that deals with the occurrence, movement, distribution, and properties of water on the Earth. Hydrogeology is the branch of geology that studies groundwater, aquifers, and the movement of water beneath the Earth's surface. Groundwater originates mainly through infiltration and percolation of rainwater into the subsurface. Water occupies the pore spaces and fractures present within rocks and sediments, forming groundwater reservoirs called aquifers. Aquifers are geological formations that store and transmit groundwater. There are four major types of aquifers. Unconfined aquifers have a water table exposed to atmospheric pressure and are directly recharged by rainfall. Confined aquifers are enclosed between impermeable layers and contain water under pressure. Perched aquifers occur above the main water table due to the presence of localized impermeable layers. Artesian aquifers are confined aquifers where water rises naturally due to hydrostatic pressure. Now let us discuss the major river basins and groundwater provinces of India. India possesses several important river basins. The Ganga Basin is the largest river basin in India and supports a significant proportion of the population. Other important river basins include the Brahmaputra Basin, Godavari Basin, Krishna Basin, Narmada Basin, Mahandi Basin, and Kaveri Basin. Groundwater provinces of India are broadly classified into alluvial aquifers of northern India, hard rock aquifers of peninsular India, coastal aquifers, and Himalayan aquifers. One of the most important concepts in hydrogeology is Darcy's law. Darcy's law was proposed by Henry Darcy in 1856 and describes the movement of groundwater through porous media. According to Darcy's law, the rate of groundwater flow is directly proportional to the hydraulic gradient and the cross-sectional area and inversely related to the resistance offered by the medium. Mathematically, Q equals K multiplied by I, where Q represents discharge or flow rate. K represents hydraulic conductivity. A represents cross-sectional area. And I represents hydraulic gradient. Darcy's law is valid only under laminar flow conditions and homogeneous porous media. Hydraulic conductivity refers to the ability of soil or rock to transmit water. Its value depends upon porosity, permeability, grain size, and fluid viscosity. Materials such as gravel and coarse sand possess high hydraulic conductivity, whereas clay exhibits very low hydraulic conductivity. Groundwater levels do not remain constant and exhibit periodic fluctuations. These fluctuations are influenced by rainfall, recharge, evaporation, pumping, land use changes, and seasonal variations. During the monsoon season, groundwater levels generally rise due to increased recharge. Excessive withdrawal of groundwater causes lowering of the water table. Groundwater tracers are substances used to determine the movement and origin of groundwater. Common tracers include tritium, carbon-14, chlorine-36, fluorescent dyes, and stable isotopes. Groundwater tracers help estimate recharge rates, flow direction, and contamination pathways. Excessive extraction of groundwater can lead to serious environmental consequences. One such consequence is land subsidence. Land subsidence refers to the gradual sinking of the ground surface due to depletion of groundwater reserves. Examples of land subsidence have been reported from Mexico City, California, Jakarta, and several regions of India. Another consequence of overexploitation is deterioration of groundwater quality. Groundwater quality is determined by physical, chemical, and biological characteristics. Important parameters include pH, total dissolved solids, hardness, salinity, nitrate concentration, fluoride, arsenic, iron, and microbial contamination. Groundwater pollution occurs when harmful substances enter aquifers and contaminate water resources. Major sources of groundwater pollution include industrial effluents, sewage discharge, landfill leachates, agricultural fertilizers and pesticides, mining activities, and seawater intrusion. Contaminated groundwater poses serious health hazards and affects ecosystem functioning. Now let us discuss the Gibbon-Herzberg relation. one of the most important concepts in coastal hydrogeology. The Gibbon-Herzberg relation explains the equilibrium between freshwater and saline water in coastal aquifers. According to this principle, freshwater being less dense floats above saline water. For every 1 meter rise of freshwater above sea level, approximately 40 meters of freshwater extend below sea level. Thus, Z equals 40 multiplied by H, where Z represents the depth of freshwater below sea level and H represents the height of the water table above sea level. Excessive pumping of coastal groundwater disturbs this balance and results in seawater intrusion, making groundwater saline and unsuitable for drinking and irrigation. Therefore, sustainable management of groundwater resources is essential for maintaining water security. For UGC NET examination, remember the following important concepts. Distribution of water on Earth. Hydrology and hydrogeology. Types of aquifers. Major river basins and groundwater provinces of India. Darcy's law and its assumptions. Hydraulic conductivity. Groundwater fluctuations. Groundwater tracers. Land subsidence. Groundwater quality and pollution. Gibbon-Herzberg relation. Seawater intrusion in coastal aquifers. These concepts are frequently asked in UGC NET and JRF examinations and are extremely important for understanding groundwater resources and their sustainable management. Let us begin with natural resources. Natural resources are materials and substances obtained from nature that are useful to humans and support life and economic development. Based on their renewability, natural resources are classified into renewable resources and non-renewable resources. Renewable resources are replenished naturally over time and include solar energy, wind energy, water resources, forests, and biomass. Non-renewable resources are finite and require millions of years for their formation. Examples include coal, petroleum, natural gas, and mineral deposits. Resource exploration refers to the process of locating and evaluating natural resources using geological, geophysical, and geochemical techniques. Resource exploitation involves extraction and utilization of these resources for industrial and economic development. Although resource exploitation contributes to economic growth, excessive and unscientific utilization causes serious environmental problems. Mining activities lead to land degradation, habitat destruction, deforestation, and soil erosion. Combustion of fossil fuels releases greenhouse gases and contributes to global warming and climate change. Industrial activities generate pollutants that contaminate air, water, and soil. Overexploitation of groundwater leads to depletion of aquifers and land subsidence. Deforestation and habitat fragmentation result in biodiversity loss and ecological imbalance. Therefore, sustainable resource management is essential for balancing economic development and environmental conservation. Historically, rapid industrialization and increasing population have accelerated the depletion of non-renewable resources. Since these resources are finite, conservation becomes extremely important. Conservation of non-renewable resources involves efficient utilization, recycling, reuse, technological innovations, and development of alternative renewable energy sources. The principle of sustainable development emphasizes meeting present needs without compromising the ability of future generations to meet their own requirements. Now let us discuss natural hazards. Natural hazards are extreme natural events capable of causing damage to life, property, and the environment. When these hazards affect vulnerable populations, they result in disasters. one of the most destructive geological hazards is earthquakes. Earthquakes occur due to sudden release of energy along faults and plate boundaries. Seismic waves generated during earthquakes cause ground shaking, structural damage, and loss of life. India is highly vulnerable to earthquakes, particularly the Himalayan region and northeastern states. Volcanic eruptions are another catastrophic hazard. Volcanoes release lava, ash, gases, and pyroclastic materials that can cause widespread destruction and atmospheric disturbances. Landslides involve downward movement of soil and rocks under the influence of gravity. Heavy rainfall, earthquakes, deforestation, and human activities increase the probability of landslides. The Himalayan region and Western Ghats are particularly susceptible to landslides. Floods are among the most frequent natural disasters in India. Floods occur due to excessive rainfall, river overflow, dam failures, cyclones, and poor drainage systems. Floods affect agriculture, infrastructure, and human settlements. Drought is a prolonged period of deficient rainfall leading to water scarcity and reduced agricultural productivity. Arid and semi-arid regions of India are especially vulnerable to droughts. Avalanches are rapid movements of snow and ice down mountain slopes. They are common in the Himalayan region and pose serious threats to human life and infrastructure. Tsunamis are giant ocean waves generated mainly by submarine earthquakes, volcanic eruptions, or underwater landslides. The Indian Ocean tsunami of 2004 is one of the most devastating examples in recent history. Cloudbursts are localized events characterized by intense rainfall occurring within a short duration. They frequently occur in mountainous regions and often trigger flash floods and landslides. Prediction and monitoring of hazards play a crucial role in disaster risk reduction. Earthquake monitoring is carried out using seismographs and seismic networks. Remote sensing and geographic information systems, commonly known as GIS, are extensively used for hazard mapping and vulnerability assessment. Meteorological satellites help predict cyclones, floods, and drought conditions. Hydrological models assist in flood forecasting. Early warning systems significantly reduce casualties and economic losses. Mitigation refers to measures adopted to minimize the adverse impacts of hazards. Structural mitigation measures include dams, embankments, retaining walls, earthquake-resistant buildings, and slope stabilization techniques. Non-structural measures include land use planning, hazard zonation, disaster preparedness, awareness programs, and emergency response systems. Community participation and capacity building are equally important components of disaster management. The disaster management cycle consists of 4 phases. The first phase is mitigation, which focuses on reducing risks before disasters occur. The second phase is preparedness, which includes planning, training, and early warning systems. The third phase is response, involving rescue, relief, and emergency operations during disasters. The final phase is recovery, which includes rehabilitation and reconstruction after disasters. For UGC NET examination, remember the following important concepts. Classification of natural resources. Resource exploration and exploitation. Environmental impacts of resource utilization. Conservation of non-renewable resources. Sustainable development. Major geological hazards including earthquakes, volcanoes, floods, landslides, droughts, avalanches, tsunamis, and cloudbursts. Hazard prediction techniques. Remote sensing and GIS applications. Early warning systems. Structural and non-structural mitigation measures. Disaster management cycle consisting of mitigation, preparedness, response, and recovery. These concepts are highly important and frequently asked in UGC NET and JRF examinations. Thank you for being a part of this learning journey through Unit 4, Environmental Geosciences. Throughout this unit, we explored the origin and internal structure of the Earth, minerals and rocks, plate tectonics, Earth's energy budget, climate of India and ENSO, weathering and soil formation, geochemistry, groundwater resources, and natural hazards. Understanding these concepts is essential not only for success in the UGC NET and JRF examinations, but also for appreciating the complex interactions that govern our planet and sustain life. Environmental geosciences provides the scientific foundation for sustainable resource management, disaster mitigation, water conservation, and environmental protection. Remember, conceptual clarity is the key to cracking competitive examinations. Focus on understanding processes rather than memorizing facts, and always connect different topics to develop an integrated understanding of Earth systems. I hope this lecture series has helped strengthen your concepts and made your preparation more systematic and effective. If you found these lectures useful, continue revising regularly, practice previous year questions, and stay consistent in your preparation. Thank you for learning with Rush Learning Hub. Keep exploring. Keep questioning. Keep learning. And most importantly, keep believing in yourself. I wish you all the very best for your UGC NET and JRF journey. May your hard work, dedication, and perseverance lead you towards success. Thank you once again. See you in the next unit. Happy learning.